Okay. So in the previous recording, we talked about the common emitter stage and its equivalent with a MOSFET, a common source stage. We looked at the basic amplifier where it was just one transistor and a resistor to convert the current from the drain or collector terminal into a voltage. And then we looked at a slight variation to that stage where the source or emitter was connected to a resistor, an additional resistor. And we analyzed the small signal circuit, and we learned about a new way of analyzing these transistor circuits without going into all the small signal analysis mode. And we saw that, okay, if we know our basic stages, we can probably reduce, I don't know, 70 to 80% of the transistor stages into those, and then use the tables that we have for the formulas in order to solve them. Now, in this lecture, we are going to talk about two additional stages. They are called for PNP or NPN transistors. They're called common collector or common base stages. And the MOSFET equivalents are, of course, common drain and common gate stages. Very similar to each other when you use a MOSFET or BJT. We are going to analyze the BJT case first, but I'll show you the MOSFET equivalent and the formulas for the MOSFET equivalent at the second stage. And I think as a good practice for you, you can go and do the small signal analysis for these stages and then confirm that the MOSFET formulas that I show you are basically what you get from a proper small signal analysis. So what we want to do is that we start with a common collector stage. So going into the naming convention that we introduced in the last lecture, we expect that the collector now is the common terminal between the input and output. So in other words, collector is your AC ground. The input is applied to the base. We know that we never applied the input to the, we never applied take the output from the base. So if you are taking collector as the common terminal, then the input has to go to the base and output has to come from the emitter. So if you look at the circuit, it's probably going to look something like this. The input is applied to the base. Here is my input. I need some biasing here that we will talk after this discussion. This is the biasing voltage. Let's just call it V bias. You just provide enough bias so that you get the desired IC that gives you the GM that you want for AC performance. And then the signal is applied to the base, output is taken from the emitter, but as usual, again, we have a controlled current source. We want to convert that current into a voltage, so I use a resistor to do the task of converting a current into a voltage, and this is my V out. Okay, so this is a common collector amplifier. The equivalent MOSFET stage will look like this. So you will have an RS here, V out here, and the MOSFET that is sitting between your source and a biasing voltage. Okay, so these two are going to behave very similarly. Of course, both transistors are going to be in their active region of operation. By now, we know that that's the requirement for making an amplifier. So I'm going to focus on the BJT part for now. Common collector, because the collector, if you look at the AC performance, is going to be your AC ground. The input is between base and ground. Output is taken from emitter and ground. And therefore, your collector is the common terminal between the two. The other name for this stage is emitter follower, or in case of a MOSFET, it's called the source follower, and we'll see in a second why that is. So I'm going to put it in brackets, emitter follower. And let's do the typical thing. So what I want to do is that I want to find the gain, the input resistance, and the output resistance. And why do I want to know this stuff? Because I want to go back to that triangle with an input resistance and a controlled source and an output resistance, which makes my life so much easier, as we saw in the discussion for the common emitter stage. So I'm going to solve this using the small signal analysis techniques that we know by now. The small signal equivalent circuit, I draw my transistor first. Emitter is connected to a resistor and then the ground. This is my output voltage. The collector is connected to VCC, which is AC ground, so that's the collector end. And base is connected to my small signal source and a DC source where it is zeroed for my small signal analysis or AC analysis, right? So that's the small signal circuit. I want to figure out gain, input resistance, and output resistance. So again, to remind myself, input resistance is measured here, and output resistance is measured from here. Okay, so let's do the gain analysis first. V out, if I look at this circuit, is the current that goes through the resistor times the resistance. So I can write V out like this. V out is the current that goes through the resistor is made of these two components, the current coming from the collector and the current coming from the base. So it is V pi over R pi, that's the current coming from the base, this current, plus GM V pi, now it's this current. They add up at the emitter node, go through the resistor, so multiply by RE, that gives me the voltage at the output. Looking at that voltage, I notice that I don't know V pi. So I want to find an equation that relates V pi to V in, and it looks like that if I write a KVL here, that will do the trick. And this is actually the same as the analysis we did with the common emitter stage and an emitter resistance. So this should be familiar, but just to go through the process again, V in is V pi plus VE, but VE in this case, or plus V out in this case, right? So I already know what V out is. I can plug it in directly into here, so it is just V pi times 1 plus 1 over R pi plus GM times RE. Okay? And again, from the discussion that we just had, we know that 1 over R pi, this term, right, is beta GM over beta, because R pi is beta over GM, so this is GM over beta. And then when you add GM to GM over beta, this term is negligible, because beta is usually much, much, much bigger than 1. So at the end of the story, I can combine these two equations and write V out as a function of, V pi as a function of V in, and then finally V out as a function of V pi. So V out is going to be eventually, and again, I'm going to ignore this 1 over R pi factor here when it is added to GM. So this 1 over R pi I ignore here, this 1 over R pi I ignore here. It gives me simpler equations. So it's going to be GM RE times V pi, and V pi is found from this expression here, divided by 1 plus GM RE times V in. Or from here, I can see that the voltage gain, if I divide the output to the input, is GMRE over 1 plus GMRE. Okay. So right away, you have to have a little bit of concern when you see this expression here. If you look at that expression, it's GMRE, some positive number, divided by 1 plus GMRE, meaning that the voltage gain is less than 1, always, right? You can make it close to 1 if you choose a large GMRE. Let's say if you choose a GMRE of 10, you can make it 10 over 11, 0.9. It's close to 1, but it's always less than 1. And that is somehow contradicting the expectation we had from an amplifier. From an amplifier, you know, it is in the name. You amplify the signal, but in here the voltage amplitude has dropped. We still call this an amplifier. So I would like you to pause for a second and think, you know, what can happen here? Why do we still call this an amplifier if the voltage gain is less than 1? If my voltage at the output is going to be smaller than the input? And why would I need a circuit like this if the voltage is just smaller than the input? I'm not gaining any voltage gain here. So pause for a second, think about why I may still call this an amplifier, or I still do call this an amplifier. Okay, so the reason is that, go back to the definition of amplifier. We said an amplifier increases the signal power, right? And for electrical signals, the power is measured by multiplying the voltage and current of that signal. So it's VI that is the indicator of the signal power. We looked at the voltage gain, but we didn't look at the current gain. Now, how do I figure out the current gain? In order to figure out the current gain, I short circuit the output terminal to ground, right? So the output terminal is short circuited to ground. I measure the I out here and compare it to the current that goes in. What is their expectation? I'm short circuiting the emitter terminal to ground, and I'm looking at the ratio of the emitter current to the base current. What is your expectation? What should that ratio be? If you said beta plus 1, you're right. So let's do the calculation from the small signal point of view. So I out in this case is going to be V pi over R pi plus GM V pi, right? So the current from the left side plus the current from the right side. However, V pi, if I set the emitter, if I make the emitter grounded, V pi is equal to V in. So it's going to be V in times 1 over R pi plus GM. And if I want to look at the current gain, I need to see how much current is going in. So it is V pi over R pi. So actually I could just take this as the current gain I in, right? So what I can do here is maybe rewrite this. I can say it is V pi over R pi, so factor that out. V pi over R pi times 1 plus GM R pi, okay? And this is my IN. So from here I can see that my current gain, which is I out to IN, is 1 plus GM R pi. And then noting that R pi is beta over GM, this is 1 plus beta. As you might have expected, I'm looking at the ratio of the emitter current to the base current because I'm shorting that RE out, right? I'm looking at the output current. So it is true that this circuit doesn't give you a voltage gain, but it has plenty of current gain, you know, easily a factor of beta plus 1. And then when you look at the power gain, now it is, you know, AV times AI. And definitely it can be much larger than 1 in practical situations. Nonetheless, it is a bit curious, right? So if I wanted the current gain of beta, you know, common emitter would have given it to me. It has a current gain of beta. But on top of that, a common emitter stage has a voltage gain of larger than 1. So why would I use a common emitter stage? Well, let's keep going with the analysis here and see what happens when we calculate the input and output resistances. If I want to solve this circuit for input resistance, again, I notice that my source V in this case doesn't have a output resistance, and therefore if I remove that and attach a test source in its place, I'm going to have the same circuit. Now also I notice that this is exactly the same as the circuit that I solved for common emitter, right, with emitter degeneration there, because in that case I had a resistor past the current source, but that resistor doesn't show up in my equations in the input. What I'm trying to do here is to basically reuse the information from the past. If you do the calculations or go back to your calculations for common emitter, you can at the end of the story show that V in over I in, or just look above, right? V in over I in for this circuit is going to be R pi times 1 plus GMRE. So this is the same calculation that we had for common emitter, right? So as soon as you put the emitter degeneration there, your input resistance went up by a factor of 1 plus GMRE. So that's good, right? It increases the input resistance for a voltage source. For a voltage amplifier, I would like to have a large input resistance. But again, nothing that different from a common emitter stage with emitter degeneration. So it just looks like I'm losing on the gain without gaining anything on other aspects so far. Let's look at the output resistance for this circuit as well. So for output resistance, I need to redraw the circuit with the source now attached to the output. So let me draw the rest of the circuit first. Collector is grounded. GM V pi here, plus and minus V pi here. This is my R pi. RE is here. The source that I had at the input is now removed from the circuit. And looking at where I'm measuring the R out, I need to attach my test source to that node. So this is where I have my test source. Let's call it Vy. My goal is to figure out what is Iy as a function of Vy, and the ratio of the two will give me the output resistance when I look back in here. All right? So let's see what is Iy. If I look at this circuit, Iy has a component that goes this way, and this is the same node, a component that goes this way, and a component that goes this way. Right? So those three currents will give me Iy. So this one that goes down here is easy. This one is just the voltage drop across the resistor over the resistor. So this is Vy over Re. Okay, so that's that. The current that goes to the base, if I look at that current, it's V pi over R pi, but V pi over R pi is flowing this way. I'm looking at the current that is going the opposite direction. So that is going to be minus V pi over R pi. And then the current that goes to the right side here, this is, again, I know the current in that branch is GM V pi, but it is going in the opposite direction. So again, it is going to be minus GM V pi. All right. So I have Iy as a function of V pi. I want Iy as a function of Vy, right? So I look at the circuit again. Let's see if I can make sense of this and figure out what it is. I look at the voltage here. The voltage here is Vy. I'm directly connecting the source to that node, to the emitter of that device. Well, look at the circuit. V pi here is measured from base to Vy. Vy is from base to emitter. Vy in this case is from emitter to base. So by looking at that circuit, I can see that Vy is, or V pi is minus Vy, right? V pi is measured from here to here, but Vy is measured from here to ground. So V pi is equal to minus Vy. Or you can write your KVL from here and go through here to ground and then convince yourself that's the case. Now, if I know these two, I can show that Iy now is going to be Vy times 1 over Re. The negative sign that I had for V pi in that equation now goes away. It becomes positive, and same thing for the last expression. And therefore, I can calculate R out, which is Vy over Ry. Now, I'm going to make one more simplification here. Remember, R pi is beta over Gm. So 1 over R pi is much smaller than Gm. I'm going to ignore that term. It's going to be 1 over Re plus Gm. Okay. So that's R out. Is it big? Is it small? It's hard to say. So let's do one modification. Gm is transconductance. The unit for Gm is current over voltage, or Siemens, right? So let's define a resistor that is 1 over GM. A resistor value that is 1 over GM, right? So GM is amps over volts. I flip it over, it will become volts over amps or ohms. So let me call Rm and define it as 1 over GM. Right? It's just a variable that I use to make that equation look nicer in a second, of course. And in that case, then I can show that R out is 1 over Re plus 1 over Rm. Okay? And Rm being 1 over Gm. Well, look at that expression. It's like two resistors put in parallel. One resistor is Re, one resistor is Rm. So this is Rm in parallel with Re. Now I can get a sense of this output resistance, right? How? Gm for 1 milliamp of current is about 40 millisiemens, right? So therefore, for 1 milliamp of current, Rm is going to be 25 ohms. When I look at this combination, R out, that is Rm in parallel with Re, let's say if your bias current is 1 milliamp and your Re is hundreds of ohms or several kilo ohms, your combination Rm in parallel with Re is definitely going to be less than 25 ohms, right? So remember, when you put two resistors in series, the combination is larger, always larger than each one of those. When you put two resistors in parallel, the combination will always be smaller than each one of those. So in this case, the output resistance, you can always say that this is less than Rm, regardless of the value of Re. Even if Re is less than Rm, that expression is correct. Now, what does that mean? Because Gm for BJT is fairly large. 1 over Gm is going to be small, or Rm is a value on the order of tens of ohms in most cases. The output resistance here for this stage is tens of ohms. And that's great news, right? Because I wanted a voltage amplifier to have a really small output resistance. For typical resistor values that I have for electronic circuits, my range of values are between 100 ohms to maybe 100 kilo ohms for 80% of my resistors. And if I get resistors on the order of 10 ohms, 20 ohms or so here, it's a small resistor. I'm getting a small output resistance out of this amplifier. And this is where we value the common collector stage, right? We like it because of its small output resistance. Where do we use it? Well, if you look at the combination of the properties, it has a gain that is about 1, close to 1, right? So GMRE is usually a number around, let's say, 10, 20 or so, or maybe even larger, right? So the gain is around 1. An input resistance that can be fairly large, and an output resistance that can be really small. It has a good current gain as well. So I have a current gain that is large, a voltage gain that is about 1, a large input resistance, and a small output resistance. So it ticks 2 of the 3 boxes that I wanted from a voltage amplifier. It has a large input resistance and a small output resistance. It doesn't have that much of a gain. Like common emitter, it ticked 2 of the 3 boxes as well. It had a large voltage gain, a large input resistance, but unfortunately the output resistance was large. So you, again, give and take. So again, we have to give up on the value of voltage gain, but we get a very small output resistance. Where do I use a common collector stage? Or its equivalent with MOSFET common drain stage, where I need to drive a load that is relatively small. So if your RL is a speaker, it's an 8 ohm resistor. If you connect it directly to a 1 kilo ohm resistor of a common emitter stage, you will get nothing out of that amplifier. Do that exercise at home. I think actually there is a problem in your textbook that looks into this. So I'd like another stage that buffers my amplifier, the voltage amplifier that I have at the beginning that is sitting between the microphone and, let's say, the speaker. I want to buffer that amplifier stage from this low resistance load. And I use a common collector stage here. So I get all the voltage gain that I want from my common emitter stage, let's say, but then I isolate it from the load, and I get the small output resistance that I need from the load perspective from a common collector stage. For that reason, this stage is also called a buffer. Right? So a buffer doesn't give you voltage gain. It just isolates two parts of the circuit from each other. It doesn't let one part of the circuit to affect the preceding stage that much. In this case, the load and your amplifier. It just buffers. It just monitors the voltage from one input to the output. Or the other way of saying it is that the voltage at the output follows the voltage at the input. And hence the name for this stage, emitter follower. The emitter voltage follows the base voltage. And we call it an emitter follower or source follower if you're using a MOSFET. So this is a very useful stage, again, if you have to drive a load that needs a lot of current. Small resistance, right? So some other cases that you may need this is if your source has a very large output resistance. So let's say some microphones may have a capacitive output, and then that is a large output impedance from your source. You cannot really connect it to a, let's say, common emitter stage that has a relatively small input resistance because then all of your signal will drop on the output impedance of the source. In this case, sometimes you may want to put a buffer in between the source and your main amplifier. And then in this case, what you do is that you take the voltage from the source, you show the source a very large input impedance, monitor that voltage, take it out, and then you put a second amplifier stage after it that can now work with the source, in this case with low output resistance, right? Okay, and now if you look at a MOSFET equivalent for this circuit, a common drain circuit will look like this. We just drew that. I'm going to draw the small signal analysis and just write the equations for this. You are suggested to solve it. So V in and V out here. And this is VDD. Again, the device is in active region, so you go and draw the small signal equivalent circuit. Drain is grounded, source is down here, RS, V out here, GM, VGS. Now GM in this case is a GM of a MOSFET. And then the DC source here goes away for small signal circuit. V in, V out, input resistance is what I see when I look this way, output resistance is when I look back. Okay? Now I want to figure out what is R in, R out, V in, and voltage gain. Now, I'm not going to go through the full solution. I suggest you do, but you can also maybe cheat a bit and use the results that we had for common emitter stage. Remember that, you know, from the small signal point of view, the analysis looks the same when I take R pi and push it to infinity. Now, if you do the analysis or go and use the BJT problem, the BJT solution, you can show that V out over V in, as I said, very similar to what you had here. It's going to be GMRS over 1 plus GMRS. So again, the gain is less than 1, but GMRS can be much larger than 1, so that the gain is almost 1. R in is going to be what? Infinite, because you're looking into the gate, which is an open circuit. And R out, if you do the calculations, it's going to be RS in parallel with 1 over GM for the MOSFET. In this case, it's the GM for the MOSFET, right? Or you can call it RM as before. And again, you can see that this can be a small value. Now, a buffer that you make with MOSFET has right away some advantages to a buffer that you make with the BJT, right? R in is infinite for a MOSFET. The gain value will be a bit less because MOSFETs generally have a smaller GM than BJTs. But, you know, for a MOSFET buffer, you expect a gain of, let's say, 0.7 to 0.9. For a BJT buffer, you expect a gain of maybe 0.9 to 0.95 or 0.8 to 0.95, something like that. So you lose something on the gain side when you use a MOSFET, but you gain a lot on the input resistance side. It's just infinite. You cannot really match it. Output resistance is going to be a bit more than what you get with the BJT, and again the reason for that is that 1 over GM for a BJT is going to be smaller than 1 over GM for a MOSFET under more or less similar conditions. So that's that. The next topic is now going to be maybe one example. So let's go through one example here. So this is a typical situation that you know what you want from the AC performance side and you go and design your DC circuit according to that. So the question says that let's say we have a common collector stage. That is driven by a source with an output resistance. And this R source is 100 kilo ohms. Okay? Now the question here is, determine IE and beta minimum such that R in is 100 kilo ohms and RE, which is actually the other way of saying RM, slightly different but is 10 ohms. Okay? So they are using a buffer here. What they care about is R in and R out. And R out, we said, has an upper limit of RM or RE, and that is 10 ohms. I don't want the output resistance to be more than 10 ohms. And I need an input resistance of 100 kilo ohms, so at least I get half of the signal showing up at the input of this transistor. So what I can do is that I can go back to my formulas and recall that R in is 1 plus GM RE times R pi. Okay? And then RM is 1 over GM, or RE is almost 1 over GM. So let's just assume they're equal. If this is 10 ohms, I can start from here. Because I know GM is IC over VT, so this is going to be VT over IC. If this is 10 ohms, then I can calculate IC, because VT at room temperature is known. So if I use the equation or the information from the problem, so it's 25 millivolts divided by IC. And right away I find an IC that is 2.5 milliamps. Okay? In reality, the difference between RM and RE is that RE is going to be beta over beta plus 1 times RM. Right? So it's the difference between IC and IE. It's the resistance that I see when I look up. In most cases, it's negligible. So I'm going to ignore it for now. But if you want to be super accurate, you can go and assume that RE is that equation and solve it like that. So that's that. I will have IC of 2.5 milliamps. And then from that, I can actually go and find what is the value of GM. So I have a value for R in, so 100 kilo ohms, is equal to 1 plus GM. GM for 2.5 milliamps is going to be IC over VT, so 2.5 milliamps over 25 millivolts times RE. What was the value of RE in this case? RE is 1 kilo. So this was given. So that times RE, so that's 1 times 1 kilo times R pi, which is beta over Gm. So times beta over Gm, and then again Gm is this value here. Let me just calculate Gm for this value. Gm is IC over Vt, and that is going to be 0.1 for these values of voltage and current. So let me just use that value directly here. So this is 0.1 times 0.1. I want R in to be at least this much, so R in has to be larger than this, so I can calculate the beta min from that expression. So 100 kilo ohms should be larger than this, is going to give me a factor of 100, so 101 divided by 0.1 times beta min, and therefore you can see that beta min is going to be sorry, this has to be this way. So this value should be larger than 100 kilo ohms, right? So beta min or beta has to be, I can calculate beta min. I can just look at the border here. So this is equal, so beta min has to be 10 to the 4 divided by, let's say, 10 to the 2. 101 is almost 10 to the 2, so that's 100. Or beta has to be larger than 100, okay? So that's, if you're choosing a transistor here, you want to choose a transistor whose beta is larger than 100, so that you get an output resistance of about 10 ohms for 2.5 milliamps of current, and an input resistance of about 100 kilo ohms for an RE of 1 kilo. Okay. And on your slide 28, there are examples of cases where you need to use a common collector stage. Have a look at that. We already covered it, and then I'm hoping that you can follow the discussion easily. Now, the last topic to discuss before we go into the biasing issues is the common base stage. So this is the last of your 3 basic stages, or the equivalent MOSFET is obviously going to be called common gate. And in this case, what we have is, again, common base, meaning that base is common between the input and output. Obviously, the input cannot be collected to the collector. We discussed it before. So collector is the output and the emitter is the input. So if I draw the circuit, the AC circuit, it's going to look like this. You have your input attached to the emitter, and output is from the collector. And obviously, we use a resistor here to convert the current from the collector into a voltage. Okay? So this is the circuit. And again, we do not include, or we did not include biasing here, but just make sure that you remind yourself that there is always some proper biasing here to keep the device in the active region. So this is your common base stage. We want to analyze this circuit. Go draw the small signal equivalent circuit. Okay? And then the input and output resistances are measured from here to here, and obviously in this case when I look up. So this is R in and that's R out. For on the small signal circuit, well, I have a base that is grounded, the source that is appearing here, and a resistor that is grounded here, and V out. R in is measured this way, and R out is measured from here. Okay, so I want to find out V out, V in, sorry, V out over V in, which is my voltage gain, and my input and output resistances for this circuit as before. So I look at the output circuit, I see that, like many times before, V out is just minus GM V pi RC. I'm going to go through this analysis a bit more quickly because I'm sure by this point you have had enough experience with the small signal analysis. V pi, I look at this circuit, I notice that V pi and V in are applied between the same two nodes, but V pi is minus V in, right, in this circuit, because, look at this. The positive terminal of V pi is connected to the negative end of V pi. V in is connected to the negative end of V pi. So V pi is minus V in. And therefore I can show that V out is minus GMRC times minus V in. Okay? So two negatives cancel each other, so the voltage gain is going to be GMRC. Well, look at that. We had a common emitter stage without the emitter degeneration that gave us a gain of minus GMRC. Now we have a common base stage that gives me a gain of positive GMRC. So it looks like that if that negative sign is bothering me, I have an alternative circuit. But we said common emitter is used 80% of the time if I want some voltage gain or maybe more. So let's see what is wrong with this stage. It gives me the same value of gain, but what about the other parameters? Okay, so the first thing I do is that I look at the input resistance. So I measure I in. Again, you can go and attach your test source, take out V in and attach your test source, but it's the same thing. So let me calculate I in. I in this case, I can see that there is a current that goes this way, current that goes this way. So I in, the current that goes to the left side is going to be V pi over R pi. But V pi over R pi is flowing in this direction. I'm looking at the current that is going in the opposite direction, so it's minus V pi over R pi. And the current that goes to the right side here, it's GM V pi, but opposing direction again. So this is again minus GM V pi. And right a second ago, I noticed that V pi and V in this circuit are essentially the negative of each other. So I can show that this is V in times 1 over R pi plus GM. And going from the discussions in the recent past, I know 1 over R pi is almost negligible compared to GM in most situations. And therefore, I can calculate R in as the ratio of V in to I in to be approximately, if I ignore 1 over R pi, 1 over GM. But we gave this a name, RM, right? So the input resistance is RM, and this is the aha moment, right? I do not use this stage as a voltage amplifier in all cases because RM is small. We just talked about it. It's on the order of 10 ohms or tens of ohms in typical situations. That is small compared to the typical resistor values that I need. So this is the drawback, right? I got the same gain, but the input resistance is small. And if I want to calculate the output resistance here, of course I have to redraw the circuit for that analysis, because now the circuit is different. The voltage source is applied to a different location. Sorry, in this case I have the input removed, base grounded, plus and minus V pi, R pi, GM V pi here, and then over here I have RC and my test source. And then we have done this a few times already. V pi is 0 in this circuit, you can see it. 0 at the top of R pi, 0 at the bottom of R pi, so V pi is 0, therefore GM V pi is 0, and therefore all of I goes through RC, and quickly you can show that R out is just RC. Okay? So I have an amplifier, a voltage amplifier, that has a good gain, GMRC, can be tens or hundreds, has a small input resistance, and an output resistance that is the same as a common emitter stage. So this, compared to a common emitter, has a much smaller input resistance, almost the same gain, and the same output resistance essentially. As a voltage amplifier, I don't really like that small input resistance part that much. And so for that reason, whenever I want to have a voltage amplifier, usually common emitter is the first that I go to. Now here is another issue. If you look at the current gain for this device, or for this stage, in this case what I do is I short circuit the output to ground and I measure this current, right? So in here I short circuit this to ground and I measure this current. If you look at that, it's going to be beta. And again, this is not hard to see why. Sorry, not beta, alpha. So it's going to be beta over beta plus 1. Right? And it's not really hard to see why without even analyzing the circuit. You're pushing a current into the emitter, you're taking the current from the collector, you lose a little bit of it to the base, right? How much? Beta over beta plus 1 is the ratio of the collector to emitter current, right? It is almost 1. We know beta is really large, but it is less than 1. So you don't get a lot of current gain here. And again, going back and comparing it to a common emitter stage, with a common emitter you had a current gain and a voltage gain. In this case your current gain is 1, but the voltage gain is significant. However, you are also giving up input resistance if you go from common emitter to common base. So the question is, why would anybody in their right mind use a common base stage? And the answer to that is that it has some other properties that make it superior to a common emitter stage in practical applications that are beyond what we are covering in this course. But two of them are, first of all, it has a better high frequency response. So if you have a high frequency signal coming in, let's say a 100 megahertz signal or a gigahertz signal, a common emitter stage has a smaller bandwidth than a common base stage. So usually you go and use a common base stage if you want to have some amplifier, some voltage gain right away. So that's one problem, one advantage of common base stage to common emitter stage. And in that case, actually, the small input resistance is helping you. Because in RF systems, your impedances are always around 50 ohms, 75 ohms, depending on the standard. But they are relatively low, the impedance of the characteristic impedances of your systems. And the low input impedance of the common base is not really a limitation in those situations. So the extra bandwidth that you get with this stage is very beneficial. So you use it instead of a common emitter stage. Another advantage that common base has compared to common emitter is that if the voltage at the collector changes quite a bit, very large changes at the collector end, the breakdown voltages that you can have for the junctions if you use a common base stage is higher than a common emitter stage. It gives you a little bit more room for the variations of the collector to input voltages. That is not a concern again in most practical applications, at least those that you are dealing with. But for example, this was a situation for CRT drivers, the cathode ray tubes that you used in TVs and oscilloscopes in the past. Now, so altogether, common base is probably the least used stage at low frequencies. The common emitter stage is used for its high voltage gain, high current gain, high input resistance. The drawback with that stage was the large output resistance. The common collector stage or emitter follower stage, we love it because it has a very high input resistance, a small output resistance, and it gives us some current gain, but the voltage gain is about 1 or slightly less than 1. And common base stage has the high voltage gain and the same output resistance of common emitter, but a very low input resistance. And for that reason, at low frequencies, we don't really use it that much. Now, the similar stage for a MOSFET is going to be a common gate MOSFET stage. So You can go and do the analysis, and you can show that the gain is GMRD for that stage. The input resistance is 1 over GM for that stage, and the output resistance is RD. And the current gain for a MOSFET common gate stage is 1. It's not less than 1, it's 1. Think about it for a second and convince yourself that you expect that from a MOSFET. So with that, we are done with the discussion on basic amplifier stages. And there is a table in your slides and in your textbook, and I also provided samples of the final exams from previous years that has all these properties of these 3 stages summarized, right? So the common emitter, common base, and common collector stage, you have values for the input, output resistances, as well as the voltage and current gains that you can use to maybe skip the full small signal analysis in some cases. If you can reduce a complex circuit to one of these known stages or a combination of them, then you can reduce that stage to just 1 input resistance, 1 output resistance, and 1 gain value, and simplify your circuit analysis. Very, very helpful in terms, especially when you have a multi-stage amplifier. But in general, a small signal analysis will get you to the right result if you do it right. So if you do not, and I actually strongly recommend you to do a few small signal problems to solve a few first, then come back and use these formulas for the analysis of the circuit. And in that case, we draw the AC circuit, which is basically the same circuit as the large signal, with all the capacitors shorted, all the DC sources removed, and we use the knowledge that we have about the basic stages to solve those circuits. So that's that, and the next topic for our transistor amplifier stages is going to be the biasing, and then I will also solve a few amplifier stages during our live sessions. So make sure that you attend those if you would like to ask questions during the live sessions. Otherwise, I'll try to answer or solve a problem that is requested by people that are attending that session.